Hey guys, it's Andrew here, and in the last video we were taking a look at the significance of a digit's position in a base 10 number. So again, we were dealing with, say, at the base 10 system, so 0 through 9, right? And we had a number, say, I don't know, 7, we went with 7, 6, 3, 3, let's switching up, 7, 5, 2, 4, right? So 7,524. We could even make it a little bit bigger here. Let's make it 67,524. And each of these each of these decimal positions, getting a little ahead of myself, each of these decimal positions had a given value for each position. So starting all the way over here on the right, this, again, base 10 system, we're going to make this column here was our ones column. So a base 10 system, we're going to raise this to a power of 0, which makes this the ones column. And if we'd made this second column here on a base 10 system a power of 1, that is a column of 10, right? And then this guy would be 10 to the second power, which is the hundreds column. 10 to the third power, right, is the thousands column. Kind of squeezing this in here. And 10 to the fourth, right, is the 10,000 column. Okay, we could try to draw a little column like this. All right, so we had each of these different column sections, right? We can kind of divvy this up, and this column here is, we take this our digit value. So in this case, on our base 0 through 9 base 10 system, 6 times its given position value, right? And this position holds a value of 60,000, right? And then this holds a position of, I'm going to try to squeeze this in here, kind of scroll down here. So 7,520, and 4 times 1 is 4, right? And then if we took each of these positions, right, for their given value, and we took the sum of all of these positions, we would get our 67,000, sorry about that, 524, okay? So depending on the position of our decimal value in our number, our positional argument, we can determine what each of those values is, and then we can take the sum of all those values and get our total number, right? Just kind of a roundabout way of showing us, you know, that a 6 in the 10,000s place represents 60,000, right? And 7, 5, 2, 4, all right? Down the list we go. And that is a base 10 system to give us some type of reference. But now we're looking over at a binary system. Okay, so binary. Now, this bi part is going to be our key indication here that this is a base 2 system, all right? So instead of a base 10 system where we went 0 through 9, this is base 10, all right? Base 2 is going to be based on a 0 or a 1, okay? Now, we could get into the, like the digital logic or, the electronics behind this, and we might say that this is an off value and this is an on value. This might be considered false, right? We'll actually look at this when we get into the ANDing process later on, when we get deeper into subnetting our actual IPv4 addresses and our IPv6 addresses. But we'll, false or true, right? For different values, right? A 0 or a 1. For now, we're just simply going to look at this and we're going to say each of these is going to represent a bit, all right? So in binary, a 0 or a 1 is a bit of data or a bit of information. And if we have 8 of these bits, okay, we're going to have 1 byte. All right, so maybe you've heard, like, say, you download a music file, right? So got a little musical note here. So an example here, let's say we have an MP4 file, right? We have some music or a music video, and it's roughly a couple megabytes in size. theoretically, right? And short video, okay? And it's a few megabytes in size. Each of those megabyte, one of those, or a couple of those megabytes are going to be a million of those bytes collectively, and each of those bytes has 8 bits in it, and each of those bits is going to be either a 0 or a 1, something that our computer can easily understand, all right? So now we are going to look into using this base 10 system, right? The way we went about converting one of these numbers in a base 10 system. We're going to also be able to take this same number line of saying we have 10 raised to the 0th position, 10 raised to the 1st, 10 raised to the 2nd, 3rd, 4th, and so on and so forth in a base 2 system. Where we're going to have 2 raised to the 0, 2 raised to the 1st, 2 raised to the 3rd, and so on and so forth. So when we come back, we're going to build that number line. So we have our binary values, right? We have our, let's see here, our base 2 system. All right, so we're moving away from that base 10. We're going over to a base 2. And we have our 0s and our 1s. Okay, sweet. And we have these numbers. So let's build a number line just like we did before with our base 10 system. And let's start sticking in some of these 0s and 1s and see what happens. All right. So I'm going to build a system, and I'm going to build a small number line to start, and then we'll move up to something a little bit bigger. Okay. So before, let's see here. Remember, starting on the right, before I had a 10, right, I would have 10 raised to the 0th power. But now, we're actually going to do something a little bit different, right? Not 10 raised to the 0th power. Let me just wipe this up here. Okay. It's going to be 2. All right, it's the base 2 system, so 2 raised to the 0th power. All right. Then the next position will be 2 to the 1st. All right. The third position here would be 2 to the 2nd. And then we'll go up to 2 to the 3rd. All right. And we're going to make a little table just so it's a little bit easier to see. Okay. So excuse me if this isn't too straight. All right. And let's make a table. Let's make some lines here. All right. And I'm actually going to continue these lines down. And you'll see why in a bit. All right. We'll just kind of stick this in here. So for now, we've got our base 2 system. All right. And each of our base values is going to have some number representation. So again, this is some basic exponents here. So 2 raised to the 0th position is going to be a value of 1. Now remember, and then 2 raised to the 1st, or 2 times itself, is 2. And again, in exponents, 2 times 2, so 2 times 2, 2 times, right, is 4. All right, and 2 times 2 times 2, or 2 to the 3rd, is 8. All right. So again, not perfect, not like our base 10 system, but we now know that in this column, if we have any values inside this column for our binary value, it's got a decimal equivalent of 1. All right. Just as before, if it was a 10 system, right? If we had like 10 raised to the 0th power, it's still 1. In the last example, we had 10 raised to the 1st here, right? And that was 10, 100, 1,000, so on and so forth. But now, again, base 2 system, so 2 to the 1st is 2, 2 to the 2nd is 4, 2 to the 3rd is 8, and so on and so forth down the list. We'll look in just a little bit here. So what would happen if I took these binary values here, all right, and I shoved them in down here, okay? So let's see what happens, right? Now let's say I've got a 1, a 0, a 0, and a 1. All right, so I put a 1 in this most significant column all the way to the left, or the position 2 raised to the 3rd, or with a decimal equivalent of 8. I put a 0 here, a 0 there, and a 1 here. So remember, before we would say, well, let's take this column, right, and we're going to multiply our binary, before we would take our, our decimal value, so if we said this was the 7, we had, remember, I'll just make it small right here, use a different color, right? I said we had 7, 6, 3, 3, right? And this was 10 to the first, 10 to the second, 10 to the third, that's a 3, I swear, 10 to the third, all right? And I would take this value and I'd say, all right, well, this is the thousands position, so 7 times 1,000 means that this positional value is 7,000. And then 6 times 100 makes this position 700. Well, this time we're going to take it, we're going to say, well, let's take this decimal value and multiply it by 1, or we're going to take this positional value and multiply it by 0. All right, it's the binary system. So a little bit of a twist. So let's see what happens there. Let me grab the color here. And we're going to say, so 8, right, times this positional value in binary is a 1, plus 4, it's a 4, times 0, and then a 2 times 0, and a 1 times 1. Okay, and if we add these all together, we get 8, oops, 8, it's bad 8, my bad, plus 0, plus 0, plus 1 equals 9. So in binary, we can derive that 1001 has a value of 8 and 1, all right? So let's break this down. Let's make this chart a little bit bigger and see if we can't, count in some bigger numbers. All right, so I'm going to make a bigger number line. Now, I just wanted to show you that small number line so we can see the process of building up our base 2 system. We're going to do it again here, and I'm going to go through the same steps. But remember, I mentioned something earlier about this byte, right? Or a bit, we have 8 bits in a byte. So we have 8 total values. 8 of these bits equals 1 byte. All right. This is going to be a lot more significant when we get into counting IPv4 addresses, as we'll see each of those values, like 192, 168, so on and so forth, has 8 bits of data in that little chunk, or 1 byte. All right. So let's build a binary number line here, or binary table, if you will, with 8 bits of data. All right. So again, we're going to say, pick the same colors again. So we're going to lower this down a little bit here, and we're going to say this is, again, base 2 to the 0 power, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, 2 to the sixth, and 2 to the seventh. All right. Try to space that out nice and neat for you. And we're going to kind of draw our chart here. All right. Let me draw these lines a little bit longer, just like last time. Extend these guys out here a little bit. Excuse the drawing. Okay, so we got our chart. Now let's raise our values, right? So 2 to the 0th value in this far right position is a decimal value of 1. 2 to the first is 2. 2 to the fourth, 2 to the second is 4. 2 to the third, so 2 times 2 times 2 is 8. 2 times itself 4 times, 16. 2 to the fifth is 32, so we can see our numbers going up quite a bit. 2 to the sixth here is 64, and 2 to the seventh is 128. All right, so in a 8-bit system, 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, 8 total values, right? 8 bits is 1 byte. So this is the decimal breakdown of 8 bits of data, or 1 byte. All right, so and then depending on which combinations of zeros and ones we use in these different positional values will derive us a different decimal value. All right, and then looking ahead, we'll be able to actually take that decimal value and work backwards and derive the binary equivalent of that value. And this is actually much of what our routers will be doing in our Cisco devices when they are determining which subnet our computers are operating in. All right, going to be going through this binary conversion for us. All right, we're just going to put in the decimal, but you know, it's good to see, and it's going to be important for us to be able to understand exactly what's going on. So let's just take an example here, and let's stick in some values. All right, so let's say I was, my computer spit out a number here in binary, and we said it was 1, 0, 1, 0, 1, 0, 0, 0. Right? Now, if you didn't know about this chart, right, and you just kind of looked at it and, you know, like, what is that? But now we know that each of these positions has a distinct positional value. So once again, I'm going to take my decimal value up here and multiply it by my binary value. Okay? And we're going to do that for each and every column. And you're going to see over time, essentially what it's going to work out to be is if a 1 exists in this positional value, right, in this column, then we are going to implement, we're going to see that 128 is part of the sum of our values, right? If we have a 0, 64, or whatever position isn't. But let's walk through it anyway. So I'm going to take 128, all right, 128 times 1, all right? We're going to put it in parentheses here because we want this to be enclosed within this column here. We're going to move on. Now this isn't going to line up perfectly, but 64, all right, times 0, all right, and then we're going to add 32 times 1, 16 times 0, all right. Stay with me here. 8 times 1. Running out of space. 4 times 0. My bad, guys. I ran out of space. So we're going to kind of wrap this down right around here. I'm going to cheat a little bit. And then we're going to say plus. Right? 2 times 0 plus 1 times 0. All right. So what does this all equal? Well, it would equal this 128 plus, well, that's a 0. We can skip that. Plus 32. All right. And that's a 0. Plus 8. All right. So 128 plus 32 plus 8. You can add these together, so our 2 makes us 130, 160, 168. All right. So we can see, based on this given number line here, we should probably shift this over a little bit, but given this number line, we can actually, the number table, and we can actually, given some set of binary values, we can derive its decimal value. All right, let's take a look at this one more time here. All right, we're back here, okay? So let's try this again, right? So let's say we have a binary value of all ones. So this will actually show us a little bit of foreshadowing into the future. And you may have seen something like this before, all right? So again, if I have all ones, I can say that each of these columns, so 128 times 1, 164 times 1, 32, 16, 8, 4, 2, 1, right? Since it's going to be a 0 or a 1, it's either going to be a value that is used or a value that isn't used, I can kind of skip over that step of me saying, we got, let's say 128 times 1, right? Because anything times itself is going to be itself, or anything times 0 is going to be 0, right? So we can actually skip over this step at this point. And we can just say, if there's a 1 in this column, we're going to use it, right? So 128, we got a 1, plus 64, plus 32, and you see where this is going, plus 16, plus everything, right? Plus 8, plus 4, plus 2, plus 1. And I'm going to spare you all the math here, and we're going to say it's 255. All right? So we can say that if we have all 1s in this column, right, we're going to have all 1s in all 8 bits of our byte, right? Our maximum value is going to be 255 in decimal. If, for instance, we also had all 0s, well, you can pretty much guess what this is. It's 0, right? If we have all 0s, it's 0. So our total range is going to be 0 in binary here, right? When we're dealing with 1 byte of data here, we're going to have 0 ranging all the way to 255. And you've probably seen this if you ever built a subnet mask, right? You've ever seen an IP address and they give you a whole string of characters and numbers. You might have seen 255 repeated multiple times, 255.255.255. Well, that 255 is all 1s in binary, all 1s in 1 byte or 8 bits of data. All right, so just a little foreshadowing what we're going to be doing in the future with that subnet mask. We're going to see that we can actually convert it to a binary value and then manipulate it later. All right, and then we'll actually see how the computer or our routers take those values and given a subnet mask, we'll actually be able to do some basic digital logic to derive what is our network, where our network begins, where it ends, and we're going to be using this whole binary process. So quite a bit of information here, right? So in the next video, we're actually going to be taking some of these values here. We've seen that we can go from binary to decimal, but what about the other direction? What would happen if I was just given a decimal value and I said, go find the binary, right? So we're going to work backwards through this equation, and we're going to be able to determine, given some binary number, right, say 231, sorry, some decimal number, not binary number, some decimal number, say 231, how do we figure out what its binary equivalent is? All right, so I'll see you guys in the next video when we look at that.